Okay, so in this video, we're going to talk about measures of central tendency. And measures of central tendency are basically mean, median, and mode. So this is something that you have probably heard about at some point in your life before this point. But we're going to discuss it from a more statistical point of view, more in depth than what you're used to. And I think you'll learn a few things about mean, median, and mode that you probably haven't thought of before. So with that being said, a measure of central tendency, when we say that, we mean it's a value that represents a typical, or what's the center of a data set. What's typical to come out from this data set? And because of that definition of what's typical, it's important that we use a correct measure of central tendency when we report it. For example, if I report the mean of a data set opposed to the median, I should pick the measure of central tendency that is the most truthful, that represents the data set as closely as possible. So with that being said, what is the mean? Well, the mean, and you probably know this by now, but the mean is the sum of the data entries divided by the number of entries. And because this is statistics now, we are going to be talking about the difference between a population mean, which is denoted by the Greek letter mu, and the sample mean, which is denoted by an x bar. They're both calculated the same way though. So to calculate the population mean, we add all of our data entries together. So x is a data entry, and we divide by a capital N, and capital N is the population size. Sample mean is the same thing. We add together all of our data entries, but we divide by a lowercase n, and we should remember that that is sample size. And remember that population mean and sample mean do have different symbols. So make sure you realize that they do have different symbols, and that you should know what represents what. Okay, the median of a data entry is simply the middle, like the median of a road, right? So if you order a data set from least to greatest, the median is going to be that middle number. And if there is no middle, because you have an even number of data entries, what you do is you average the two middle numbers, and that's your median. And then finally, the mode of a data set is the value that occurs the most. Mode is very useful if you have qualitative data, because if you don't have numbers, really you can only use the mode. For example, if I ask everybody what their favorite color is, I can't average colors, right? So I have to use the mode for a measure of central tendency. And if a data set has two modes, it's said to be bimodal, or even multimodal is another way that you can phrase that or use that word. Bimodal is typically used for only two modes. So with that being said, let's find the mean, median, and mode of this data set. So I'm going to let you do that on your own here. Find the mean, median, and mode. Okay, so you should have paused the video, found the mean, median, and mode. The mean, we have to add all the values up and divide by how many there are. And after you add them all together and divide by how many there are, I'm going to use x bar because I think this is a sample, right? This isn't a whole population. There's probably more than 7 flights for a major airline. And you get 527.9. The median is 427, because this is already from least to greatest, and the middle number is 427, and the mode is 397. So you should have gotten those values. One thing I want to point out is rounding. I always get this question, how many decimals should I round to? Well, 0.9 is what I use because my data set is whole numbers, and you should round at least one decimal place further than the rest of your data. So one decimal place is just further, this is just one decimal place, which is the 0.9. Okay, the next thing that we're going to do is review a stem and leaf plot, and this is to remind you of what an outlier is. So an outlier is a data entry that is far removed from other entries in the data set. So I would pause the video here and take time to make your stem and leaf plot and see if it matches mine. So you should have made a stem and leaf plot, and if you did take the time, you can fast forward this part, but ages of statistics in of statistics. I meant of students. Of students in a statistics class. So you should definitely have a title. 1 through 4 is our leaves, and there's a 17, 18, 19-year-old. There's 8 20-year-olds. No 30-year-olds. 44-year-old, and everybody made a key, right? Keys are very important for stem and leaf plots because you don't know if the 20, like this 2 line 0 could be 20, it could be 200, it could be 0.20. Now it's age, so it is probably just 2-digit numbers, but that's why the key is important, so we know for sure. And the outlier is a number that is farther away from the rest of the data. So 44 is an outlier in this case. And you may ask yourself, well, how do I know when an outlier is an outlier? Like 44 is pretty clearly an outlier, right? It almost doubles the highest age, the next highest age. But what about, I don't know, 40? Is 40 an outlier? 35? 30? 29? You know, you eventually, if you keep going lower, you might get to a gray area. You might say, I don't know if that's an outlier or not. Well, in the next couple sections, the last 2 sections of Chapter 2, we'll discuss some ways that you can make an outlier, or can find an outlier, and it's a more set-in-stone way of doing it. Still a little arbitrary, though, actually, but it's guidelines that we can use to find outliers. Okay? Right. Another type of mean I want to talk about is a weighted mean. And a weighted mean, we'll still use x bar as a symbol. And to find the weighted mean, we sum together the x's, which is our data entries, times our weights, and we divide by the sum of all of our weights. Okay, so for example, actually I'll explain that in a little bit. So for example, we have a class and we have 5 different sources. We have the score and we have the weights. The score is what we're trying to average. We're trying to find the average score for this person taking this class. So that's the x. And the weights is how much each score is worth, which is obviously the weights w. So many of you have taken a class like this before, right? Where each category is worth a certain amount. I don't do this. I just like straight points. So the top of our formula is x times w. So when you do have a summation like this, you do what's in the summation first, and then you add everything together. So we want to do the x times the w's first, which is what this column is for. So this column is to help us just organize our work. So we're just going to multiply across to find x times w. So 86 times 0.5 is 43. 96 times 0.15 is 14.4. 82 times 0.2 is 16.4. This one's 9.8, and this one's 5. And when you add all of them together, so again we want to sum them all together, we should get 88.6. Because that's what the sum means. And then when we find the sum of the weights, that's the sum of this column, the weights column. Well, that's 0.5 plus 0.15 plus 0.2 plus 0.1 plus 0.05, which is 1. This doesn't always happen. You don't always have a 1 as the sum of the weights, but for the purposes of finding the class grade, in this case you do. So this person's grade in the class is an 88.6, so probably something like a B+. Right? Let's do another example where the sum of the weights isn't 1, because I feel like that's kind of cheating if I just show you this one example. So let's talk about a college report card, because in college GPA is calculated slightly differently. So this is a new example. We'll just write it down because we have some space here. And in high school, you recall GPA, an A is 4, a B is 3, a C is 2, a D is 1, an F is 0. But in college, you are taking multiple classes generally, and each of these classes are worth a different number of credit hours. For example, you can have a class taking 4 credits, 3 credits, 3 credits, 2 credits. And the grade, and then you get a grade for each of these classes. So maybe you got a B, a C, and an A. Well, in college, if you get a B in a 4 credit hour class, that B is worth more than the B in the 3 credit hour class because it counts 4 times, whereas the B in the 3 credit hour class only counts 3 times. So this is a great way to prioritize your grade. So if you think about GPA, the GPA, if you just look at the grades, this should be a B average, right? Because you have 2 B's, you have a C, which is just a letter grade less than a B, and you have an A, which is a letter grade more than the B. So a B average is a 3.0. Well, if I want to calculate this GPA, is this the true GPA going to be less than 3.0 or greater than 3.0? Keep in mind and look at how many credits each grade has. So let's actually do the math, and we'll talk about how we know if it would be less than 3 or more than 3 without doing the math. So the grade for each of these is going to be 3, 3, 2, 4, because that's just what the standard GPA is. And then let's do the math. So we want to multiply the x's times the w's. Now here's the thing. What are the x's and what are the w's? Is x the classes or is x the grade? What are we averaging? Do we want to find the average number of classes or credits, or do we want to find the average grade? Well, we want the average grade, right? So that is the x, and then w is the weight. That's how much each grade counts. But in any case, we're still multiplying. So 3 times 4 is 12, and then we're going to add all of them together. So 12, 3 times 3 is 9, 2 times 3 is 6, 4 times 2 is 8. And then the bottom is the sum of the weights, which is 4 plus 3 plus 3 plus 2, which is 12. And if you do that, that's 35 over 12. The GPA is 2.92, which is a little less than 3. And that shouldn't surprise you if you thought about this correctly, because the average should be a 3, but look, I got a C, or this person got a C in a 3 credit hour class, which is worth more than the A in the 2 credit hour class. So this C is technically weighted higher than the A. So even though, if I just look at the grades, everything averages out to a B, the C carries more weight. So it should make sense that this is a little bit less than a 3.0. And those are 2 weighted GPA, or just weighted mean examples. Alright, the last thing I want to talk to you about is shapes of distribution. So there's 4 types of shapes. Now, not every distribution fits into just one of these shapes. There's many other shapes that exist, but at least I want you to know these 4 shapes. And most data sets can be described using one of these shapes, or at least a combination. So if I have a symmetric distribution and I make a histogram, a symmetric distribution looks something like this. And the mean, the median, and the mode is in the middle. So if I have a histogram, if I make a histogram of a data set and I get this, I would call this symmetric. And remember, histogram frequency is on the left. So the mean's in the middle because it's symmetric. Everything averages out to the center. The median is also in the middle because the middle's going to be in the middle, right, of the data set. And then the mode is the value that occurs the most. which is going to be the tallest bar because the mode is the most frequent. Okay, uniform distribution. All the bars are relatively the same height. So, I'll do one more bar here. So the mean, because everything averages to the middle, because you have equal amount on each side. Same thing with the median. The mean and the median are both in the middle. Now, because it's a uniform, if it's a truly uniform distribution, no mode will exist. Now, with that being said, in real life, and you make one of these histograms, in real life, the mode is probably going to exist because not all the bars are going to be perfectly level. If it's a perfectly uniform distribution, all the bars are perfectly level. But if it's not perfectly uniform distribution, which is probably going to be the case, one of these bars might be slightly higher than all the rest, and that's where your mode is, which is fine. Okay, but you would still call it a nearly uniform distribution. All right. The last two shapes I want to talk about is a skewed left distribution, which means you have a little bit of data on the left side, and a skewed right distribution. So this is skewed left because if you just look at where most of the data is, it's skewed left because you have a little bit of data on the left side. And this is skewed right because, again, you have a little bit of data on the right side. So the skewness comes from which direction the data is skewed. Where is there a little bit of extremes, basically. So in this one, the mean, median, and mode are not in the same spots. So the mode is here. The mode is here because that's the tallest bar. But think about where would you put the mean and where would you put the median. So maybe pause the video, think about it for a little bit, and then press play. Alright, so the mean, and move this down. So the mean is actually farther to the left for skewed left and farther to the right for skewed right, whereas the median is closer to the middle. And a lot of people actually have the opposite thinking. But the reason why this is the case is because the mean is more affected by outliers or by extreme data values. This actually happens all the time. So I'm going to give you a simple example here. Let's say you're driving through a neighborhood and there's a $100,000 house, a $150,000 house, a $200,000 house, $250,000 house, and then let's say there's a much bigger house that's worth let me think, let's just say 700. Let's say $800,000. Okay, so if you were to add all these up and divide by 5, if my calculations are correct, I believe you get 300. Well, where's the mean in terms of this data set? 300,000 is going to be in between the 250 and the 800. Really, the only data value that's close to 300 is 250. But remember, a measure of central tendency should be representative of the data set. It should tell you what a typical data entry is. Well, the median in the data set is 200, and really you have the majority of the data around 200. 150, 200, and 250 are all within 50 or 1,000 of the 200. Well, what's going on? It's because extreme values affect the mean more. Now, obviously, this is a smaller data set, so the 800,000 is definitely going to affect the mean more. But the same principle arises. You know, this mean is pulled farther to the right towards the skewed data. The mean is pulled farther to the left towards the skewed data. Whereas the median is a better representation of what the center is. Another example I like to give is if you Google search the average cost of a wedding. So this is the first thing that came up. You shouldn't always use the first thing that comes up in a Google search, but for our purposes, It'll do fine. And we have the average cost of a wedding in the United States is about $26,000, let's say. And then if you keep reading, it says, but most couples spend less than $10,000. So the median is actually less than $10,000, but the average or the mean is around $26,000. Well, what's going on? Why is the mean so much higher than what most couples actually spend? It's because you have these people that are spending a ton of money on weddings. You know, if they're millionaires, they might be spending $100,000 or plus on their kid's wedding, which is ridiculous. That's so much money that could be spent on something else, right? So just one day, you're blowing hundreds of thousands of dollars. So this is one example of a mean where the mean is greatly affected by these extreme values, right? So depending on what you're trying to report, like if you're trying to convince your parents to spend more money on your wedding, tell them what the average cost of a wedding is. Don't tell them the median cost. The average cost is $26,000. The median cost is $10,000, right? You want to use statistics for the better. But really what you should be doing, if you want to be truthful about this data set, is, if I were to give a measure of central tendency that really represents this data set, I should be reporting the median. Because the mean just, I think, takes this data set out of proportion and says, oh, well, people are spending a lot of money on weddings. When in reality, I mean, they still are, but in reality, it's actually typically less, right? Most couples spend less than $10,000. So, in general, what I want to point out to you is the takeaway of this is the median is a better measure of central tendency for skewed data sets. Okay, and that's section 2.3, which is measures of central tendency.